Welcome to the lecture series on CFD, Part 2. This is lecture 31 on large-eddy simulation of turbulent flows. This lecture starts with a brief description of the concept of energy cascade in turbulence and an introduction to large-eddy simulation, or LES. This is followed by a more detailed presentation of the LES framework. It includes the concept of filtering, the subgrid-scale stress tensor, and the approaches to model the effects of small scales. Next, boundary conditions used in LES are described. LES requires substantial resources for the simulation of flows at high Reynolds numbers because it needs to resolve a large part of turbulence spectrum by solving the unsteady Navier-Stokes equations on a fine grid over tens or hundreds of thousands small time steps. We discuss how and when is LES used in research and engineering. The features of LES and the challenges in its use are highlighted with two examples: simulation of flow around a smooth sphere and a sphere with a tripwire at a moderate Reynolds number of 50,000. In turbulence research, the concept of energy cascade is often used to illustrate how is the kinetic energy of turbulence transferred from large eddies, where it is generated, to the smallest eddies, where it is dissipated into heat. This is usually done by reference to the energy spectrum of turbulence, shown schematically on this diagram, representing the relation between the energy spectrum and the wave number k. Note that logarithmic scales apply to both axes. Both the kinetic energy of turbulence and its dissipation rate can be expressed by an integral of the spectrum of the wave number, as shown by these two expressions. The largest eddies in the forcing range contain most of the kinetic energy. This energy is passed on to slightly smaller eddies, and the cascade continues until the smallest eddies are reached, which dissipate the energy into heat by viscous friction. In 1922, Richardson describes this by a poem. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. In between lies the inertial range. In 1941, Kolmogorov postulated that the energy spectrum in this range must be proportional to the wave number to the power of minus 5/3, which was later confirmed by both experiments and direct simulation of turbulence. The idea behind LES is to resolve the forcing range and the larger part of inertial range, and to model only the smaller scales. This reduces the requirements for computing resources compared to DNS, which should resolve the whole spectrum, but increases the requirement compared to Run's approach, in which the whole spectrum is modeled. This plot shows flow patterns in one cross-section behind a sphere from a large eddy simulation. See slides 14 to 34 for more details. We see a wide range of resolved scales, ranging in size from the order of sphere diameter to 1,000th of it. In reality, much smaller scales exist, whose influence on the flow must be modeled. Large eddy simulation resolves large turbulent scales and models the small ones. Large scales are problem dependent and thus difficult to model accurately. This is the main advantage of LES over Run's approach, in which all of turbulence is modeled. Small-scale turbulence is more universal in character, and one can expect that it can be better modeled than turbulence at large scales. It is also assumed that the same model of small-scale turbulence would work well for more flow types. The computing effort in LES is large because one must perform a transient 3D flow simulation over many time steps, tens or hundreds of thousands. Grid quality is also important. Irregularities can produce artificial fluctuations and thus affect the accuracy of the simulation. Second-order accuracy in space and time is the minimum required. Central difference schemes for convection work better than upwind-biased ones. Large eddy simulation works with filtered variable values. The filtered velocity component ui at a location x is defined as follows. Here, G is the filter kernel. A box filter is a simple local average. Gaussian and cutoff filters are also used. x prime is the local coordinate with origin at x. The filtered variable value is effectively a local average over the filter width. The filter has a length scale associated with it, delta. Eddies larger than this size are resolved, the smaller ones are modeled. This figure shows schematically the difference between velocity variation in time in DNS and LES. The latter is a filtered version of the former. Filter width is usually taken to be the same as the local grid spacing, and the filtering operation is usually not explicitly performed, assuming that discretization schemes act as low-pass filters. If one wants to study modeling errors by grid refinement, one needs to keep the filter size constant. Otherwise, one is resolving more and modeling less on finer grids. This implies using a different model on each grid and arriving eventually at DNS when the grid is sufficiently fine. Filtering the Navier-Stokes equations produces a similar result as the Reynolds averaging. The filtered continuity and momentum equations are given here. The continuity equation is not changed because it is linear, but the momentum equation has a filtered nonlinear term, the filtered product of two velocity components that is not equal to the product of filtered quantities, as indicated by this expression. The filtered momentum equation has therefore 6 more unknowns, in addition to the 3 filtered velocity components. To be able to solve the filtered equations, we must model the difference between the two quantities. It is called the subgrid-scale Reynolds stress, defined as follows. The momentum equations solved in LES are given by this expression. Note that the convection term contains the product of the filtered velocities. The subgrid-scale Reynolds stress must account for the difference between filtered product and product of filtered velocities. The red-framed term must be expressed through filtered velocities by means of a subgrid-scale turbulence model. Also note that the term subgrid-scale Reynolds stress stems from the way in which it is modeled rather than from its nature. It represents a contribution to convective transport of large scale by smaller ones. The modeling of subgrid-scale Reynolds stresses is usually based on either the local velocity field or on its history. The models of eddy viscosity type are most widely used. They express the subgrid-scale stress tensor in the same form as the viscostress tensor, replacing the fluid viscosity with a turbulent viscosity μt as given by this expression. This term is added because the trace of the tensor on the right-hand side is 0, which is not the case for the subgrid-scale Reynolds stress. Turbulent viscosity has nothing to do with fluid viscosity. It varies by orders of magnitude within the solution domain and is a nonlinear function of the solution. Smagorinsky model is the oldest one and still the standard since 1963. In it, turbulent viscosity is computed as follows. Cs is the model parameter and delta is the filter length scale. Cs is not a universal constant. It is problem dependent and the optimal value can vary between 0.05 and 0.2. Dynamic Smagorinsky model determines the parameter Cs dynamically during simulation by comparing filtered values with two different filter sizes, usually the grid size and at twice that value. In SimCenter StarCCM+, the Weyl model is also implemented. It is of the same type as the Smagorinsky model, but has different choices for parameters. Many more models have been published in literature. Detached eddy simulation, or DES, is a mixture of RANS and LES methods. RANS equations are solved in the near-wall region where LES cannot reach the required mesh resolution. RANS models are described in Lecture 32. LES is used away from walls to capture the larger scales and their unsteadiness, which is difficult to model using RANS approach, especially wakes of bluff bodies. There are many versions of this approach. SimCenter StarCCM Plus also includes DDES, delayed DES, and IDDES, improved delayed DES. See sections 10.3.2 and 10.3.3 in the book for details on theory and various models. Boundary conditions for LES impose similar requirements to those used in DNS, described in Lecture 30. At inlet, the velocity needs to be prescribed. It should satisfy the Navier-Stokes equations and represent a true turbulent state. In most cases, the exact velocity field at the inlet is not known. There are theories for the creation of synthetic turbulence, turbulent fluctuations around a prescribed time-averaged velocity profile, but they are imperfect. Velocity at an inlet is often taken from another simulation, for example, of a fully developed flow. At the outlet, either the pressure is prescribed or all values are extrapolated. Extrapolation is usually based on an unsteady convective condition of the following form. Here, u is a velocity that is independent of location on the outflow surface and is chosen so that overall conservation is maintained. For LES of fully developed flows, periodic boundary conditions with a prescribed pressure drop or mass flow rate are often used at inlet and outlet. Periodic conditions are also often used at side boundaries, which should be sufficiently apart, for example, twice the distance over which the fluctuations are correlated. If the boundary layer at a wall is well resolved, that is, the non-dimensional distance of the first node y plus equal rho u tau delta y divided by viscosity is on the order of 1, the no-slip condition is sufficient. Here u tau is the shear stress velocity derived from the wall shear stress tau w, u tau equals square root of tau w divided by density. The variation of all parallel velocity component with distance from wall is linear up to approximately y plus equal 5, the so-called viscous sublayer. So the usual approximations of wall shear stress used to compute laminar flows can be used. If the grid does not resolve the near wall zone, wall shear stress is obtained from an additional model. See section 10.336 in the book and check this website for more details. Because LES does not need to resolve all of turbulence scales, with the same available computing resources, it can be applied to flows at much higher Reynolds numbers than DNS. This makes LES usable both in research and in engineering practice when accuracy requirements are high and cannot be met by using runs approach, and sufficient computing resources are available. LES is also used when it is necessary to better understand the physics of the flow by obtaining data runs models cannot provide. LES is especially useful in flows for which runs models are not designed, like flows which are not statistically steady, flows around bodies at subcritical Reynolds numbers, for example, sphere or cylinder, flows involving separation from smooth walls, natural convection flows, etc. We now turn attention to two examples of application of LES. Sphere is a body of the simplest geometric shape, defined by a single parameter, its diameter. However, turbulent flow around the sphere is very complex and difficult to predict. Here we are presenting LES of flow around a smooth sphere and a sphere with a trip wire at the Reynolds number of 50,000. The solution domain is adapted to experimental setup from Bakic from 2002, who performed LDA velocity measurements in a wind tunnel. The tunnel cross-section is 300 by 300 millimeters, sphere diameter is 61.4 millimeters, a billiard ball. The diameter of the stick holding the sphere in the center of the test section is 8 millimeters. The length of the solution domain is 600 millimeters, and the sphere is positioned at the center of the solution domain. Constant velocity of 12.43 meters per second was specified at inlet, and a constant pressure at outlet. No slip conditions are applied on sphere and stick walls. On wind tunnel walls, boundary layers are ignored, slip conditions are prescribed. This leads to a slightly lower velocity around the sphere than in experiment, because boundary layers at tunnel walls increase the blockage effect. This will be seen in the comparison of mean velocities from experiment and simulation in slide 30. Smagorinsky's subgrid-scale model and second-order discretization in space and time were used in SimCenter CM+ software. Fluid is air with density of 1.204 kg per cubic meter and dynamic viscosity of 1.837 10 to minus 5 Pascal seconds. The time step in simulations on fine grids was 10 microseconds. Trimmed hexahedral grids with local refinement around sphere and in the wake are used for all simulations. This plot shows longitudinal section through the coarsest grid. This table lists the parameters of the grids used. The thickness of the first prism layer was the same in all grids, 30 micrometers. The cell size in the finest zone around sphere and in the wake was 0.78 millimeters on the coarsest and 0.123 millimeters on the finest grid. In the case of a sphere with a tripwire, the local grid refinement was adapted to the expected smaller recirculation zone behind sphere. In addition, the grid had to be much more locally refined around the tripwire and downstream of it to resolve the shear layer and the separation zone downstream of the wire. This plot shows a detail of grid in a longitudinal section around the sphere. The tripwire has a diameter of 0.5 millimeters and is positioned at 75 degrees from the front stagnation point. In the local grid refinement around tripwire, the first prism layer next to wall was 10 micrometers thick and the cells were 41.6 micrometers long. Further downstream of the wire, the finest grid had twice these values. In addition to LDA measurements of velocity in a wind tunnel, Bakic also performed flow visualization in a towing tank. A billiard ball with a diameter of 61.4 millimeters was fixed on a cylindrical rod as shown in slide 14 and pushed through stagnant water. Dye was injected at two locations, 70 degrees and 110 degrees from the front stagnation point, respectively. Dye streak lines were recorded with a digital camera with a resolution of 500 frames per second. This allowed visualization of shear layer instability and transition to a turbulent wake, as shown in this photograph. We see clearly the separation of the boundary layer, the beginning of instability, the roll-up of the vortex rings, and their breakup. In one LES simulation, massless particles were added at about the same locations where the dye was injected in the experiment to produce numerical streak lines. A simultaneous side and top view are important to see the real motion. It shows that both blue and red particles, especially the latter, move a lot in circumferential direction. The circumferential flow variation is relatively slow, which means that long averaging times are required to obtain a statistically steady result, unless averaging is done also in circumferential direction. This animation shows vorticity contours in an axial section through the sphere center and rod axis. Darker color indicates higher vorticity. Note a strong intermittency in the wake. A large zone of no turbulence moves slowly away. The LES resolves vorticity structures corresponding to the grid size and larger. Smaller structures are filtered away. To perform a DNS of this flow, probably 1 billion grid points would be needed. These two animations show vorticity contours in a cross-section through the smooth sphere at x/r equal 0.5 on the left and 1.0 on the right. The locations of cross-section planes are indicated in this figure. Darker color indicates higher vorticity. The strongest turbulence is in the shear layer, as can be clearly seen in the animations. Note that outside shear layer, the vorticity is negligible. The flow is laminar. We see both large-scale slow motions and small-scale fast motions. The turbulence is obviously anisotropic in these two cross-sections. These two animations show vorticity contours in a cross-section through the smooth sphere at x/r equal 2 on the left and 3 on the right, as indicated in this plot. Further downstream of sphere, the wake moves a lot laterally and changes its shape. Large zones of intermittent or weak turbulence are present. Turbulence blobs are ejected into laminar outer zone, and non-turbulent blobs are pulled into turbulent wake. turbulence is isotropic in a large part of both cross-sections. This animation shows vorticity contours in an axial section through the sphere center and rod axis for the sphere with a tripwire. Note laminar separation at tripwire, followed by turbulent reattachment and a delayed turbulent separation from sphere surface. The turbulent wake is much narrower than in the case of a smooth sphere, and the recirculation zone behind sphere is much smaller. These two animations show vorticity contours in a cross-section through the sphere with a tripwire at x/r equals 0 on the left and 0.5 on the right, as indicated in this plot. Turbulence is more intense when the tripwire is present than for a smooth sphere. At x/r equals 0, we see highly turbulent boundary layer with intense fluctuations in all directions. At x/r equals 0.5, the boundary layer is still attached to the sphere. It is much thicker than in the preceding section, and it also reaches into the outside laminar flow. These two animations show vorticity contours in a cross-section through the sphere with a tripwire at x/r equals 1 left and 2 on the right, as indicated in this plot. The turbulence intensity is higher and the wake is shorter and more focused than in the case of a smooth sphere. In this cross-section, we see a strong turbulence in the shear layer and a much weaker turbulence inside the recirculation zone. In this cross-section, which is close to the end of the recirculation zone, turbulence is practically isotropic. The wake is no longer centered around the rod and it changes its shape all the time. These two plots show visualization of instantaneous shear stress magnitude on sphere surface, smooth sphere on the left and sphere with a tripwire on the right. The same color scale is used for the magnitude of shear stress in both plots. We see that the tripwire affects the flow also on the upstream side of the sphere, leading to a slightly higher shear stress. Immediately ahead of tripwire, the shear stress is low because the high-speed flow is deflected by the wire. See slide 22. On top of the wire, shear stress is high because the velocity gradient is high there. Downstream of tripwire, shear stress is low within the laminar part of the separation bubble. It becomes high again at the reattachment zone and further downstream in the turbulent boundary layer. The shear stress weakens again as we approach turbulent separation of the boundary layer. The total shear force on sphere is obviously larger, circa 30%, when the tripwire is present than when the sphere is smooth. However, because tripwire leads to a later boundary layer separation from sphere surface and a narrower and shorter separation zone, the pressure force on sphere is much lower, leading to a lower total drag. See slide 29. On a smooth sphere, shear force amounts to only circa 3.3% of the total drag, while with a tripwire, the shear component is circa 11% of the total force. This plot shows instantaneous pressure coefficient distribution from LES for smooth sphere performed with 3 grids from the front stagnation point to the stick at the back. For reference, the analytical expression for the inviscid flow around the sphere in an infinite environment is also shown by the dashed line. Due to the blockage effect in wind tunnel and the moderate Reynolds number, we have at the front stagnation point a slightly higher pressure coefficient than the theoretical value of 1. Over the front part of the sphere, the variation in LES is similar to that of potential flow, but the lowest value, corresponding to the location of maximum velocity, is higher and it happens earlier, at about 72 degrees from the front stagnation point. After boundary layer separation, we have a plateau in pressure coefficient on the rear side of the sphere. Even on the coarsest grid, LES produces a result which is much closer to reality than results from Run's models. Significant discrepancies in results from free grids are limited to the range between 60 degrees and 100 degrees from the front stagnation point. This plot shows comparison of pressure coefficient distribution from the front stagnation point to the stick at the back from potential flow, LES of flow for a smooth sphere, and LES of flow for the sphere with a tripwire. As already mentioned, tripwire affects also the flow upstream of it. The near wall velocity is increased and the pressure coefficient is lower than for smooth sphere. The lowest pressure is obtained at circa 67 degrees from the front stagnation point. It then starts increasing toward the stagnation point at the root of the tripwire. Over the front part of the tripwire, the pressure reduces rapidly as the velocity increases, reaching a minimum value close to the tip of the tripwire. Pressure is nearly constant in the recirculation zone downstream of tripwire. After turbulent reattachment, pressure increases up to circa 130 degrees from the front stagnation point and then remains nearly constant in the recirculation zone. The pressure recovers to a much higher level with a tripwire than when the sphere is smooth, which leads to a much lower drag than in the case of a smooth sphere. This plot shows the variation of predicted drag coefficient with time in LES of flow around a smooth sphere using 3 grids. The drag coefficient increases as the grid is refined and more of turbulent spectrum is resolved. The mean value on the coarsest grid is around 0.45, which is about 10% lower compared to 0.49 on the finest grid. In an infinite environment, a value around 0.5 is expected according to literature data. A slightly lower value can be expected in a confined space of a wind tunnel, which leads to a narrower wake. Unfortunately, the drag force was not measured in the wind tunnel. Note that RANS models predict drag coefficient between 0.145 and 0.346, depending on the model, which is far too low. This plot shows a comparison of predicted drag coefficient in flows around a sphere without and with tripwire, using LES and finest grids. Tripwire reduces drag by a factor of 3. Drag fluctuations are also smaller when a tripwire is present. These plots show profiles of the time-averaged axial velocity component from LES on the finest grid for the smooth sphere at x over d equals 0.33, 0.5, 1.0, and 1.5, along 4 radial lines, positive y, positive z, negative z. The profiles are compared with experimental data of Bakic from 2002. The velocity outside sphere wake is higher in the experiment than in LES simulation, because the effects of turbulent boundary layers on wind tunnel walls were neglected in simulation. Elsewhere, the agreement is pretty good, except at the last profile, where the experiment indicates a narrower wake than simulation. The fact that the results on the 4 lines differ indicates that time averaging has not been performed over a sufficiently long interval. When structured grids are used, averaging is also performed in circumferential direction, which requires less samples. In this case, averaging was performed only in time at every control volume. Because large-scale variations are rather slow, especially in circumferential direction, a very long averaging period is needed to obtain axisymmetric mean fields. These plots show profiles of the time average radial velocity component from LES on the finest grid for the smooth sphere at x over d equals 0.333, 0.5, 1.0, and 1.5, along 4 radial lines for positive y, positive z, and negative z. The profiles are compared with experimental data of Bakic from 2002. Discrepancies are larger than for the axial velocity component presented in slide 30, but the radial component is also almost an order of magnitude lower. These plots show profiles of the variance of axial velocity component fluctuation from LES on the finest grid for the smooth sphere at x over d 0.33, 0.5, 1.0, and 1.5, along 4 radial lines, positive y, positive Z, negative Z. The profiles are compared with experimental data of Bakich. The agreement is reasonably good, except for the latest station where the wake in simulation is wider than in experiment. In the two last sections, the profiles along 4 lines differ much more than in the preceding 2 sections. As was seen in animations in slide 21, the whole wake wobbles slowly around the rod, which means that much longer averaging times are required in these zones than around the sphere, where the recirculation zone is relatively centric. These plots show the covariance of axial and radial velocity component fluctuations from LES on the finest grid for the smooth sphere at x over d equals 0.33, 0.5, 1.0, and 1.5 along 4 radial lines, positive y, negative y, positive z, negative z. The profiles are compared with experimental data of Bakich from 2002. The agreement is reasonably good in the first 2 sections, while the magnitude of turbulent shear stress is circa twice larger in simulation than in experiment in the last 2 sections. The averaging time is not sufficient, as indicated by large differences between profiles along the 4 lines. This slide shows time average flow patterns for the sphere with a tripwire in the plane y equals 0 and z equals 0, and for the smooth sphere in the plane y equals 0. The mean flow is not axisymmetric yet, because the averaging is performed only in time, not in circumferential direction. Time averaging is performed over circa 60,000 samples for smooth sphere and about 70,000 samples for the sphere with a tripwire. The main conclusions from the LES study of flow around sphere are: for this kind of flow, even a coarse grid LES produces results which are closer to reality than results from all Rans turbulence models tested. Even the simplest LES subgrid-scale model, Smagorinsky model, produces reasonably good results for mean quantities on moderately fine grids using second-order space and time discretization. LES is able to predict the effects of small geometrical changes, here the addition of a tripwire. Tripwire increases shear drag but reduces pressure drag. The net effect is a 3 times lower total drag. Time average solution is not axisymmetric for the sphere with a tripwire. It may become so after a very long averaging period. In experiments, velocity profiles were measured only along 1 line. It is important to measure along 4 orthogonal lines to check symmetry.